See, that was the discussion. So we just recall the circuit diagram here, and yeah, let me. See, this was the circuit diagram. Okay, so see, this was the circuit diagram. That is, this is the this one, this one. Okay, it is the semiconductor. This part is the semiconductor, whereas the other part is the separately excited DC motor. And now remember, I have drawn only the armature circuit. The field circuit. This is the field circuit. And there is no connection between the field and armature as it is a separately excited DC motor. Now, while we were discussing about this, we have come across two conduction modes: continuous conduction mode and discontinuous conduction mode. These are the two conduction modes we have come across. So last class we discussed about continuous conduction mode. Actually, we were discussing, it was not complete. Still there is some more points are there in the discontinuous conduction mode to be discussed. Okay, but I will start with the equation where we have ended. So in the discontinuous conduction mode, we have derived the expression for VA. What is the expression for VA we got last class? If you recall, is Vm by pi 1 plus cos alpha plus EB by pi plus alpha minus beta. This is the expression for the voltage which is going to the armature of the separately excited DC motor in discontinuous conduction mode. Okay, this after this, okay, we have some more. See, this is the voltage here at this point. Which point? At this point, this is the voltage we got. Now this voltage we are applying to the armature of the separately excited DC motor. So if you recall the equation of the motor, that is VA is equal to EB plus IA RA. This is the expression for the voltage across the armature of the motor. This expression we got from the motor concepts, whereas this expression we got from the semiconductor concept. So both are same. Why? Because this is also the output of your semiconductor, whereas this is input to the motor. Now output of the semiconductor is nothing but the input of the motor. So both are same. Then what we are going to do is that we will compare or we will equate both this equation. Then what we will get here is that EB plus IA RA is equal to Vm by pi into 1 plus cos alpha plus EB by pi into pi plus alpha minus beta. This we got. Then yeah, we just from this expression I would like to know what is EB. So we will take EB one side. remaining all to the other side. Okay, so then we will get this thing EB by pi. Okay, we'll take into common, then pi plus alpha minus beta. Okay, so we'll send this EB towards that side, then it becomes, I think, EB was minus pi, that is equal to IA RA minus Vm by pi into 1 plus cos alpha. Okay, this is the simplification. Now we'll simplify further. What is EB from this equation? See, pi will be get cancelled, so send that pi towards right hand side. Then EB is equal to, EB is equal to what you will get here, IA RA into pi divided by alpha minus beta. So this is one term. The second term is Vm by alpha minus beta into 1 plus cos alpha. So this is the expression we got for EB. Now we will recall the previous equations. The previous equations of the EMF. So we'll just recalling here this side. We have written EB as, if you remember what we have written in terms of omega m. I would like to know what is EB in terms of omega m. So before that, we can do one more thing. Yeah, what that is here. What is EB equation? Phi Z n by 60 into P by A. Then we have done the simplification. What is the simplification we have done? As it is separately excited DC motor. So for the separately excited DC motor, your flux phi is constant. Okay. So if the flux phi is constant, then we have some advantages, and also we have some simplifications. So what is the simplification we got that day is EB is equal to some Km into omega m. I want you to recall this equation. We have done this already. So we will substitute this here. We'll substitute this here. So that implies Km omega m is equal to IA RA pi by alpha minus beta minus Vm by alpha minus beta into 1 plus cos alpha. We got this expression. Okay. Once we got this expression, what is the further thing here we need to understand is that, let me send this K towards right hand side, and also we have another expression in terms of torque. You recall the case of torque in terms of separately excited DC motor. So in case of the separately excited DC motor, I hope we remember the torque expression. If you remember the torque expression, we got one important thing. What is that thing we got is that, I will write this side. T is equal to Km into Ia. See, both this equation and this equation, we got from the expressions of back EMF and torque, which we discussed last class. So from this expression, what is Ia? Ia is equal to T by Km. So you have Ia here, so we'll substitute Ia here. Then, and also we'll send this Km towards right hand side. Then omega m is equal to, okay, Ia can be written as T by Km. So one more Km is there. So then what is the answer we get at the end is that T into, okay, T into RA into pi divided by Km square into alpha minus beta minus minus Vm by alpha minus beta into Km into 1 plus cos alpha. Yes, this is the expression we got for the speed. We got for the speed. Of course, it is in terms of angular speed. You can convert the angular speed into the actual speed by using this equation. Omega is equal to 2 pi n by 60. We have this equation also. So we will use this if necessary. We will use this equation and we will find out what is n from this. So that also we can do if necessary. Otherwise, we will just put there like this only. So this is the expression between. Now what is this equation? Now if you see here, this is the expression between the speed. This is speed omega m and torque. So this is the expression between speed and torque. Okay, of this particular DC drive. In which case, in the case of discontinuous conduction mode. Okay. Now we'll this keep this side, and we'll do one thing. We will do this analysis for continuous conduction. So for the case of continuous conduction, what is the expression of this voltage we will get, that also we will derive now. So this entire analysis which we did now till now, it is for discontinuous conduction mode. Okay. So now we'll take this here. Yeah. Okay. So the same thing that we will do this analysis for uh, continuous conduction. So for that purpose, we need the waveforms. Okay. We need this waveform. Now we will draw the same thing, or we will do the same analysis for continuous conduction. Okay, this is first I will draw the waveform of Vs. Okay, so what is the waveform of Vs here? This I will take it as pi, whereas this is 2 pi. So supply voltage is sinusoidal. Okay, this is a sinusoidal waveform. Okay, so now similar kind of expression we'll do here. So now we will draw the waveform for okay, output voltage. So we'll see that. Okay, so we'll see these things. This is pi. Okay. Now alpha is the firing angle. Somewhere this alpha is the firing angle. So at this angle, we fire thyristor number 1. So this is thyristor number 1. This is 2. Diode number 1. Diode number 2. So T1, T2, D1, D2. Okay. So now this is continuous conduction. So if it is continuous conduction, what I told last class, in case of the continuous conduction, the energy in the inductor La will not become zero. Okay, it will not become zero even when you trigger thyristor number 2. So it means when you trigger thyristor number 1 at alpha, okay, at alpha when you trigger thyristor number 1, so it is the case that in continue, I will write here in the continuous conduction mode. In the continuous conduction mode, Ia is never equal to 0. Ia is never equal to 0 in the continuous conduction mode. So Ia is always flowing. So in this direction, Ia is always there. So that's the meaning of continuous conduction mode. Whereas in case of the discontinuous conduction mode, we have seen that for the short duration of this time interval, the IA will become 0. This is what we have seen last. See, last in the discontinuous conduction mode, there were 3 intervals. You recall that. There were 3 intervals. One is from alpha to pi. Second interval is from pi to beta. Third interval is that beta to pi plus alpha. In the third interval, you have seen that IA is equal to 0. This is what you have seen. Okay, in case of the third interval. Now, in the continuous conduction mode, you will not have 3 intervals. You will have only 2 intervals. What are the 2 intervals? Is that first alpha to pi. This is the first interval, alpha to pi. From alpha to pi, thyristor T1 conducts. So T1 conducts through the motor and through the diode D1. So T1, okay. So T1 and through the motor and through D2. Okay, it is not D1, it is D2. Okay, I will just let me correct it. Okay, D2. So T1 motor and D2. So through that it makes a closed path. It makes the closed path. Through this it makes the closed path. There's a green line which I have drawn. There's a closed path for the T1 and D2. Okay. So it happens till it will continue till omega t is equal to pi. So when T1 and D2 are conducting, VA is same as this. VA is same as VS. Just apply KVL, then you will understand. This is very same as the previous explanation for the discontinuous conduction mode. So I will draw the waveform of VA, the waveform of VA for the waveform of VA for the first interval, that is from alpha to pi. So at pi, what is supposed to happen at pi? At pi, the supply voltage becomes negative. So when the supply voltage becomes negative at pi, okay, so there is a possibility that this T1 D2 may force, but uh, we have one more thing in case of the semiconductor. What is that thing? Is that there is a freewheeling diode is there. Yes, this I have drawn now. Okay, there is a freewheeling diode is also there. Okay, this freewheeling diode is there. Okay, so in the semiconductor you have this semiconductor along. So generally this freewheeling diode will be there. You have to connect this freewheeling diode. When you have to connect is that whenever the load is whenever the load is inductive load. So when you have inductive load, then the energy in the inductor will have to circulate through the freewheeling diode. So after pi, T1 D2 will not conduct because the energy which is there in the inductor will circulate through freewheeling diode. So it will circulate through the freewheeling diode. Now this purple color direction I have drawn, so that will happen through the freewheeling diode. So that is after pi. So T1 D2 will be off. So from pi less than or equal to, as it is a continuous conduction, I told you already that the current in the inductor will continue, or the current in the inductor will not become zero till you trigger the second thyristor. So you generally trigger the second thyristor at pi plus alpha. This point is pi plus alpha. So till pi plus alpha, the current will be there in the inductor. So that's called the continuous conduction. So from pi to pi plus alpha, that is second interval. So in this interval, the inductor will force the freewheeling diode to conduct. The inductor will force the freewheeling diode to conduct. Okay. So it will force the freewheeling diode to conduct. Okay. When the freewheeling diode is conducting, so the diode will behave as a short circuit. So the voltage across the short circuit is zero. So I can say this thing that this interval is zero. Okay. So this is same as supply voltage. Now in this interval, what are the things will conduct? Freewheeling diode and motor. So motor, freewheeling diode and motor. So through freewheeling diode and motor, the current will make the closed path. So in this case, what is VA? VA is equal to 0. Why VA is equal to 0? Because freewheeling diode is conducting, so it behaves as a short circuit. So the voltage across short circuit is 0. So that's it. So this is the total cycle, that from alpha to pi it is VS, whereas from pi to pi plus alpha it is 0. So from once again from pi plus alpha, from pi plus alpha. So at pi plus alpha, what you do? You will trigger thyristor number T2. So when you trigger thyristor number T2 and D1 will conduct. So once again, the cycle will repeat. So you see the cycle will repeat here. That's it. So alpha to pi it is Vs, and pi to pi plus alpha it is 0. So this is the waveform of the output voltage VA. So this was a little bit different compared with the discontinuous conduction mode, because in the discontinuous conduction mode you had three intervals. There is a third interval in which there is no current in the motor. So when there is no current in the motor, in the previous case you got this voltage EB as the output voltage in the third interval that you have seen. But in this case, there is no third interval. Why? Because it's a continuous conduction mode. So the current is always there. So when current is always there, then VA will be either equal to Vs or is equal to 0. So that's it. We got the waveform of the output voltage. Okay. Then what's next now? So for this waveform, VA, we will find out what is the average voltage. What is the average voltage? This waveform. Okay. Once again, we will follow the same procedure, that is 1 by time period. Here also time period is pi, because after pi the cycle repeats. So integral 0 to pi VA d of omega t. Uh, this is the expression we got. Now once again, we will divide this 0 to pi into two intervals. One is 0 to alpha. So this is alpha. One is 0 to alpha. Other is alpha to pi. So 0 to alpha it is 0. There is no output voltage. Then it becomes 1 by pi integral alpha to pi. So only alpha to pi you have. So what is that? From alpha to pi, what is VA value? VA value is same as Vs. So d of omega t. Okay. What is Vs here? Vs is equal to Vm sine omega t. So this is Vs. Substitute in the integration. Then it becomes VA average is equal to 1 by pi integral alpha to pi Vm sine omega t d of omega t. So if you simplify this expression, so you see what you are going to do. Let me do this simplification myself. So 1 by pi. So here Vm is there. Vm will come outside. So what is sine omega t integration? Minus cos omega t. So minus cos omega t. So from alpha to pi is equal to, so if you substitute pi, then becomes minus 1. So minus 1 plus. So Vm by pi into 1 plus cos alpha. Yes, this is the expression we got for the average output voltage, of the converter, or average input voltage to the motor. So Vm by pi into 1 plus cos alpha. This is in case of the continuous conduction. Whereas what is the expression we got for the discontinuous conduction? For the discontinuous conduction, this expression we got. You see, this expression we got in case of the discontinuous conduction mode. So you must identify the difference between both the voltage expressions. So one is Vm by pi into 1 plus cos alpha plus Eb by pi into pi plus alpha minus beta. Okay. So from this, these are the two differences you will find out. Okay. So this we got. So this is the output voltage expression in case of the continuous conduction and discontinuous conduction. Now what will happen? If it is the boundary between continuous conduction and discontinuous conduction? So what is meant by boundary? So boundary in the sense, see, continuous conduction is there. Continuous conduction. So I will write here continuous conduction mode. In the continuous conduction mode, you have three intervals. So in the third interval, IA is equal to 0. This you have seen already. Whereas in the discontinuous conduction mode, you have only two intervals. Okay. And IA is never becomes 0 in case of that. Okay. It is always more than 0 in case of discontinuous conduction mode. Okay. So now what about the boundary? What is meant by boundary between these two modes? Boundary. So what is meant by boundary is that it is neither continuous conduction nor discontinuous conduction. It means something like this, that I will just draw a waveform here for the current waveform, so that you will understand it's a normal current waveform. That, so just for example, so this you can call it as continuous conduction mode. Whereas I will draw another waveform, another picture I will draw. Now this is discontinuous conduction mode. You see why I'm saying discontinuous conduction mode is that There is this interval, you see the small interval. In this interval the current is 0, I. So in this interval I is equal to 0. You see in this case I never becomes 0. I never becomes 0 in this case of continuous conduction mode. Whereas in case of the discontinuous conduction mode, okay, discontinuous conduction mode, okay, so I think sorry that this is discontinuous conduction mode, whereas this is continuous conduction mode. Okay, continuous conduction mode. Okay, now you see here in case of discontinuous conduction mode I is 0 for small duration. Now there is another case, okay. Yes, so now you see here, there is a boundary. So I will tell you what is boundary here. Boundary in the sense, see, this is a continuous conduction mode, so the current never becomes 0. Discontinuous conduction mode, for some duration the current is 0. Now what is the boundary between these two modes is that, something like this. So here you see now only at one point, the I is 0. Remaining all points the I is not 0. Here I is never 0. Here I is 0 for some finite duration. You see here some finite duration. There is some finite duration in that case I is 0. Whereas here only this comes into the 0, just it touches 0 and it go back. It touches 0 and it go back. So this is called boundary between CCM and DCM. So this is the boundary. So this is called boundary. So I will tell you how to find out the boundary in our particular case. I will just draw that. Okay. So first interval in case of the discontinuous conduction mode, what is the range, or what is the interval? Alpha less than equal to omega t less than equal to pi. This is first interval. Second interval is pi less than equal to omega t less than equal to beta. This is second interval. Okay, first interval. Now third interval is third interval. So what is the third interval is that beta less than or equal to omega t less than or equal to pi plus alpha. So this is the third interval. So this is in case of the continuous conduction mode. Sorry, this is in case of the discontinuous conduction mode. So discontinuous conduction mode, these are the three intervals. Now coming to the continuous conduction mode, I will write here continuous conduction mode. What are the two intervals? First interval. What is the first interval? Alpha less than equal to omega t less than equal to pi. This is the first interval. What is the second interval? And only one interval. That is second interval is left. What is that? Interval. Second interval is that pi less than or equal to omega t less than or equal to pi plus alpha. Now you see now. So what is the boundary in the sense here? How to find out the boundary is that? So boundary in the sense continuous conduction mode, discontinuous conduction mode will both will interfere at this one point, or both will intersect at one point. So now you see here, when the continuous conduction mode becomes a discontinuous conduction mode, what is the condition that the continuous conduction mode becomes discontinuous conduction mode? I will tell you one condition, that in this particular discontinuous conduction mode, when beta is equal to pi plus alpha, Say for example, when beta is equal to pi plus alpha. So when beta is equal to pi plus alpha, exactly at this point, that is when beta is equal to pi plus alpha, continuous conduction mode is equal to discontinuous conduction mode. So I can say this is the boundary. This is the boundary. So boundary in the sense, see here, one thing to understand here, what is meant by boundary. So boundary means continuous conduction mode. We have seen very clear that you have two intervals, interval number one, interval number two. Discontinuous conduction mode, you have three intervals. So one interval here, which is that interval? The interval here is that this part. This part is the third interval where I is equal to 0. Now the boundary in the sense, we will make this duration, there is a duration here, finite duration is there. So for finite duration, I is equal to 0. So we will make this finite duration equal to 0, or just it makes only one contact here. Only one contact here. So we have to decrease this entire length. This entire length is there here. So we have to decrease this entire length to 0. It means this only one point. So you have to make it as one point. So to make it as one point, then this point and this point, or I will say this is A and this is B. So when A, B are equal, then only it becomes this dot. We'll just repeat this once again, that you have this duration here in the discontinuous conduction mode. In this duration, IA is equal to 0, or current is 0. Now, whereas in case of continuous boundary between the continuous and discontinuous conduction mode, this AB, it becomes only one point, that is C. So you have to make this point A and point B equal. So when A is equal to B, it becomes a dot. Whereas this line is there, this line becomes dot. When this line becomes dot, this line becomes dot when A is equal to B. Okay, so when A is equal to B, this is what is A, what is B. So we have to find out that what is A, what is B is that. So this interval, when beta is equal to pi plus alpha, then both these intervals will merge. Both these intervals will merge. So interval 2, interval 3 will merge like this. A and B, both the intervals will merge. In the sense here also, both the intervals, to merge these both intervals, then beta should be equal to pi plus alpha. So when beta is equal to pi plus alpha, then this distance will become 0. So this is the condition. We have to understand that when beta is equal to pi plus alpha. Okay, so the discontinuous conduction and continuous conduction mode both will have same, okay, same boundary. Both will have same boundary. So once we understand that beta is equal to pi plus alpha is the condition for the boundary. So now this becomes the condition for boundary, or I will say boundary condition. I will say boundary condition. When beta is equal to pi plus alpha, so this is the boundary condition. So we got the boundary condition here. Once we got the boundary condition, okay, now with the help of this boundary condition, we will go ahead with some more things. Okay, now we will recall the previous you have an equation in terms of beta. What is that equation we have in terms of beta? That's a last class expression we will recall here. That is for the discontinuous conduction mode. What is the expression for IA we got? The expression for IA we got. So recall that expression. So that expression I'm writing here once again. the expression which we got for um, IA. So IA expression we have derived last class. That expression I'm just recalling and I will rewrite here. So what is that is IA is equal to IA is equal to Vm by Z e power minus omega t minus pi into cot pi into e power minus omega t minus alpha into cot pi EB by RA into 1 minus. See, this is the expression already we got in the last class. The only thing is that you recall that expression. Cot. Okay. So this is the expression we got. This is the expression we got. This is the expression we got for IA. This is the expression we got last class itself. What is IA? So in this expression, if you recall, now this expression when at the end of two intervals, because you recall the discontinuous conduction mode, the three intervals alpha less than omega t less than equal to pi, first interval. So then pi less than equal to omega t less than equal to beta. So in these two intervals, IA is there, that is not zero. Then we have derived the expression. That expression is this. Whereas the third interval, that is beta less than equal to omega t less than equal to pi plus alpha, we have seen this thing that IA is equal to zero. This we have seen. Whereas the first two intervals, we know that IA is not equal to zero. So for that case, what is the expression we got? That I have I just put that expression here directly, which we got last class. Okay, so we got IA expression here. So in this expression, when omega t is equal to beta, when omega t is equal to beta, what is IA value? It means at the end of beta, IA becomes zero, because see here from alpha to pi and pi to beta. So from alpha to beta, IA will be there. Exactly at beta, IA becomes zero. Exactly at beta, IA becomes zero. This is what we have seen last class. And after beta to pi plus alpha, the IA will be zero, and that will be continue. And that duration is the discontinuous duration. So at omega t is equal to beta, IA is equal to zero. So we'll substitute this condition. Which condition now? This omega t is equal to beta, IA is equal in this equation. Then what I will get here for IA, okay, IA is equal to, now IA becomes zero. That just now I told you, okay, when omega t is equal to beta. See here, alpha to pi, pi to beta. Alpha to pi, we have seen thyristor T1 is conducting, whereas pi to beta, freewheeling diode is conducting. This is what I told last class. Then in both the cases, IA will be there. IA will be there in both the cases. That IA expression I have just rewritten here once again. I have just written here once again that IA expression. Whereas at beta, the energy in the inductor will become zero, so IA will be zero. So this IA will be zero even after beta also till pi plus alpha, at which we trigger thyristor number 2. So this so at this exactly beta, what is IA value? IA value will become zero. So that point we are substituting here. Then in that case, Vm by Z e power minus beta minus pi, because I am substituting omega t is equal to beta, then into cot pi into sin pi minus e power beta minus alpha, okay, cot pi sin alpha minus pi, okay, e minus eb by ra 1 minus e power beta minus alpha into cot pi. So this is the expression when we substitute this condition in this. Okay, then what's next now? Now coming to the case of boundary. Which boundary? The boundary between continuous condition and discontinuous condition. What is the condition we got? The condition we got here is that beta is equal to pi plus alpha. This is the condition. You see here now. You see now? Okay. This is the condition we got. Beta is equal to pi plus alpha. This is the condition for boundary between continuous condition, and we substitute that here. So we substitute beta is equal to pi plus alpha in the above equation. Then it becomes 0 is equal to Vm by Z into e power minus, what is beta we got? Pi plus alpha okay, into cot phi into sin phi minus e power minus pi plus alpha minus alpha, because beta is okay, into cot pi sin alpha minus pi. Wherever you find out beta, there you substitute pi plus alpha. That's it. Minus EB by RA into 1 minus e power minus pi plus alpha minus alpha into cot pi. Okay, this expression we got. Then further we simplify. So here pi minus pi will get cancelled. Then it becomes alpha cot pi sin pi. So we'll do one thing. We'll find out what is EB from this. So we'll take EB one side, the remaining all to another side. So EB by RA into 1 minus e power minus, here you see here this pi plus alpha minus alpha, alpha will get cancelled. So minus pi cot pi. Now you send the remaining towards right hand side. Then Vm by Z e power. So pi will get cancelled. So minus alpha cot pi minus alpha cot pi sin pi minus e power pi cot phi sin alpha minus pi. Okay, this expression we got. Then we simplify this further. Then what is EB from this equation? EB is equal to, okay, we'll send this RA and everything towards right hand side. Then Vm RA by Z into e power minus alpha cot pi sin pi, okay, minus e power minus pi cot phi sin alpha minus phi whole divided by 1 minus e power minus pi cot pi. So just only mathematically we just rearrange the terms here. Then once again. So once again, what is EB? We know EB is equal to Km omega m. This we got already. So then what is omega m then? Omega m is equal to, so send this Km towards right hand side. Then it becomes, I will just rather than writing once again, I will just copy this here. So omega m is equal to, just send this Km towards right hand side, then it becomes Km. Yes. So we got omega m is equal to this expression we got. Now this is the condition. Remember, now this is the condition for the boundary. It's very important. Okay, then I will do one thing. I will add here C, MC. What is MC? Omega. It is the speed at boundary condition. So only to represent that thing, we put here this thing. So we got two expressions for omega m. Now you see this expression for the boundary condition, whereas we got another expression, if you recall, this one, omega m. So we got two expressions for omega m. It's very important. Okay. So using this expression, we'll draw the graph between speed and torque. We'll draw the graph between speed and torque. Okay. So what is the expression for speed and torque for this case? Let me take speed on one side, torque on another side. So you see now yourself, omega m is here, T is here. What about the remaining things? The remaining things are Vm by alpha minus beta into Km, okay, into 1 plus cos alpha. We have got this expression, okay. We have got this expression here. Okay. So now you see here, important thing is that, okay, so what is the graph you will get here is, you will get several graphs for different values of alpha. So I will draw here. See, omega m t. So it is nothing but a straight line. It's a straight line. Okay. So, but that straight line, okay. So how you will do here is that, now one more thing you can understand here. Means it's better that I will rearrange this equation once again. What is that rearrangement is that? See, alpha minus beta is there. Which is higher generally, alpha or beta? You see the waveform. I want you to see the waveform of the here. Yeah. Yeah, you see here now. Somewhere I have drawn the waveform. Yes, see this now. This is alpha, whereas this is beta. Because beta is equal to pi plus alpha for boundary condition. Or beta will be here, whereas alpha is here. So always beta is more than alpha. So when beta is more than alpha, I will write here. You must understand this thing that beta is always greater than alpha, greater than or equal to alpha. Okay. Rather than writing equal, I will simply write beta greater than alpha. So when beta greater than alpha, this alpha minus beta will be negative value. So it will be negative. So then to arrange this once again, just this mathematical arrangement, then I will rewrite omega expression. What is omega m expression? Omega m expression is equal to, yeah, I will write here negative. So it becomes beta minus alpha. So this becomes negative, whereas this becomes positive. So Vm by beta minus alpha into Km into 1 plus cos alpha, 1 plus cos alpha. Okay, 1 plus cos alpha minus T into Ra into pi by Km square into beta minus alpha. Okay, so what you must understand here is that so now once we rearrange this expression, I will just draw the graph here once again between omega m and torque. Okay. So we'll do one thing. First, we'll make it as t is equal to 0. We'll draw points. So we'll make, if you make t is equal to 0, then what is the expression? It is left here, this side, this part. This part is left. So we'll start with t is equal to 0. Then what is this value? This is a positive value. Beta minus alpha into Km into 1 plus cos alpha. So that value, so alpha is there. So once again, it depends on alpha. It depends on alpha once again. Okay. So whereas if you see at the condition of boundary where beta is equal to pi minus pi plus alpha, then here in the denominator pi plus alpha minus alpha, so both will get cancelled, then it becomes only pi. So Vm is constant, pi is constant, Km is constant, then it's a function of only alpha. It's a function of only alpha. So when alpha is equal to 0, it will be cos 1. So we'll do one thing, that once again I will just take this expression and we will substitute beta is equal to pi plus alpha, a boundary condition. Then what is the speed? It becomes Vm by, so beta is equal to pi plus alpha, so alpha will equal to Vm by pi into Km into 1 plus cos alpha minus TRA by Km square. Now beta is pi plus alpha, so alpha minus alpha will get cancelled. This pi is there, so pi and pi both will get cancelled. So that's it. So it's only left like this. So pi will get cancelled. So now for this expression we'll draw once again. Okay. Now we will draw the graph now. So every case we'll draw. We are simplifying this as much as possible. Nothing else is there. So now we'll start with t is equal to 0. When t is equal to 0, what is left here? Vm by pi m, Vm by pi into km into 1 plus cos alpha. So now it means it depends upon alpha. So now we will take the alpha values, different alpha values we will take here. For example, I will take alpha is equal to 0. If I take alpha is equal to 0, then what is omega m? It becomes omega m is equal to Vm by pi km into 2. This is for alpha is equal to 0. Let me take another value of alpha. So another value of alpha, I will take it as some 30 degrees. Then if I take 30 degrees, then so let me represent this one first of all. For alpha is equal to 0, where is omega m? Omega m will be somewhere here. This height is how much? 2 Vm by k pi m. So I will write here 2 Vm by k, sorry, km into pi. This is the point. Now we'll take alpha is equal to 30 degrees. In that case, what is omega m? It becomes Vm by pi km. What is cos 30? Root 3 by 2. 1 plus root 3 by 2. So 1 plus root 3 by 2. So 1 plus root 3 by 2, it becomes, yeah, root 3 by 2 is, so just, I want to make it as accurate value. So divided by 2. Yes, it becomes 0.866. So 1 plus 0.866 in the sense 1.866. Okay. So now you see this now. What you have to understand here is that, see this case when alpha is equal to 0, what is omega m? 2 Vm by pi km. Whereas when alpha is equal to 30 degrees, what is its value omega m? 1.8666 Vm by pi km. So this value, the second value is less than the first value. So the second point I will put here. Now the third point is that when I take alpha is equal to some 60 degrees. I mean, I'm going to increase the value of alpha. Then in that case, what is the answer? We'll get omega m is equal to Vm by pi km into yeah, 1 plus 1 by 2. So 1.5. So if so the point further will decrease. So what I want to say here is that when I increase the value of alpha, this height decreases. You take every time once again alpha is equal to 0, then you go on increase the value of theta, then you get one expression like this. When alpha is equal to 30, the expression will be, the graph will be like this. When alpha is equal to 60, further increase alpha, then so you will get several graphs here. So this graph is for alpha is equal to 0, this graph is for alpha is equal to 30, whereas this graph is for alpha is equal to 60. Okay, so these are the different graphs between omega and t for different values of alpha. This is the speed torque characteristics. Speed torque characteristics of the single phase semi-controlled converter fed separately excited DC motor. Okay, so now you don't get only one graph, you get several graphs. It depends upon the value of alpha. One thing you must remember here is that when you increase the value of alpha, the graph comes down. It means the omega m value coming down. Okay, this is the thing you must understand. Now we will draw another graph between voltage and firing angle. Okay, then we'll take the expression for Va, which we got for the continuous conduction mode, that is Vm by pi into 1 plus cos alpha. We got this value. Okay, yeah, for this we'll draw the graph between, this is Va, whereas this is alpha. So for different values of alpha, you find out what is Va. Let me take alpha is equal to 0. If I take alpha is equal to 0, then what is Va? Va is equal to Vm by pi 2 Vm by pi, because alpha is equal to 0, 1, so 2 Vm by pi. So now let me take alpha is equal to some 60 degrees. Then Va is equal to, so cos 61 by 2, so 1.5 Vm by pi. So you see the graph will decrease like this. So when I increase the value of alpha, the VA value will decrease. So let me draw the graph here. Something like this, it decreases. So somewhere when VA is equal to 0, for example, let me take alpha is equal to 180. Let me take the case. So at this case, what is VA value? VA is equal to Vm by pi into 1 minus 1. So 0. So at this point, VA is equal to 0. What is that angle? 180. So it is 0, 60. So likewise, you go on increase the value, then you will get the graph like this. So this is the angle. This is the graph between voltage and firing angle. Okay.
So is it linear, sir?